Hello, my name is Erin Lawson. Today I will be teaching a lesson on logarithms. Who's responsible for logarithms? John Kepler versus Joseph Burke. John Kepler created logarithms in 1914, and Joseph Burke published his in 1620. One approach was algebraic and the other approach was geometric. Both men had something in common. They wanted to change multiplication and division into addition or subtraction. The winner is John Kepler. He discovered it in 1614, Logarithm came from the Greek word logo, meaning proportion, ratio, or word, and the end, which is algorithms, means number, together meaning ratio number. His purpose was to discover, for the discovery was to assist in science. His definition of logarithm was, the logarithm, therefore, any sign, is a number of very nearly expressing the line which increase equally in the meantime, while the line of the whole sign decrease proportionally into that sign. Both motions being equally timed and the beginning equally shifts. John Kepler and Henry Burgess. Henry Burgess helped Kepler modelize this concept of logarithm into a modern form. Natural logarithm, which is something that they created together. The comparison would be between 2 points moving the straight line. The L point, which L stands for logarithm, moves from negative infinity to positive infinity. The X sign moves, the X, which is sign, moves from 0 to infinity at a speed proportionally to the point's distance from 0. Common logarithm discovered to create a generalization and rise to a power of the values of x point corresponding to addition and multiplication of the values of the L point, which again is logarithm. The relationship between logarithms and exponentials. Logarithms are considered to be the opposite of exponentials. Just as addition is the opposite of subtraction and multiplication is the opposite of division. Logarithms or logs are the inverse of exponents. The relationships for exponents in terms of log is N equals B to the X is equivalent to log X equals N. On the left side, which will be up here because I didn't have enough one, is using exponential. On the right side is a logarithmic statement, which could be announced log base B equals N. And up here is also an example. Inside of equations, B is the base for both. If you notice, there's a B here and there's a B here. Is the base for both the exponential and logarithm. Information inside the log X is the argument. Of course, Y, or in this case N, is the answer to the equation. Example. third equals 8. The base, which would be 2. The exponent is 3. And the answer is 8. To calculate this, you would do 2 times 2 times 2, which gives you the answer of 8. This is exponential form. Logarithm form. Log 2. The log of 2, 8, 3. The base, which would be 2. The logarithm would be 8. The answer would be 3. That's logarithm form. Next, we're going to convert between exponential and logarithmic forms. Number 1, write the logarithmic equation in exponential form. A, log base 3 of 81 equals 4. So, first we'll write the problem down. Log of 3, 81 equals 4. And if you remember exponential formula, it would be 102 y equals b to the x. The logarithm form would be log of b, y equals x. So basically here, you will look and see that we're using logarithm form, and you would just basically put in the formula for exponential and basically plug and chug. Plug and chug meaning you will find the y from this formula, which would be 81, equals the b equals b. B for this formula would be the base, which is 3. And x, and the x for this one is the answer for the logarithm one, which would be 4. So basically the answer for A is 3 to the 4th power equals 81. B, you use the same concept. Log of 7 log base 7, 1 over 49 equals -2. Basically, plug and chug as before. The y, which would be 1 over 49, equals the base, which is 7, and x is -2. So it will be the log, it will be 7 to the negative 2 power equals 1 over 49. That's the answer for B. The second part states, write the exponential equation in logarithmic form. We will do the same thing except we will do the complete opposite since it's already in exponential form. A states 7 to the 3rd power equals 343. You will match it up to these two equations and you will see that it's in exponential form. So you will write down the log equation. Log base of b, y equals x. So you will plug. First you write down log. Your base for the exponential form is right here. So it will be 7, the base is 7 for this problem. Y, which would be your answer, which equals x. Your x will be 3. And that's your answer. Last but not least, B. Six squared equals 36. Again, write the formula or equation below. Plug and chose once again. The base would be, match it up, would be 6. So it would be log of 6. Y, match it up, it will be 36 is equal to x, the x will be 2. So log base of 6, 36 equals 2. And that's it. Graphing logarithm. The basic thing about graphing logarithmic functions is it would be, again, go back to exponents. It would be the opposite of the exponential form. See here, we have y equals 2 to the x. You will flip it or reverse it so that it will be log 2 to the x. If you look here, the coordinates are the same except that they're opposite, they're backwards. Instead of 0, 1, you will have 1, 0. Instead of 2 to 4, you will have 4, 2. And if you look at the table down below, you will see that the values for x and y basically just switch in reverse. So that's how you would graph logarithmic functions. Two useful log bases, which would be common logarithms, which is simply written as log n, and is known to have, if you find an equation that has just log n, you'll commonly think that the base will be automatically 10. And natural log, or base of e, which is known as the natural log of x, means the base e log. Natural log e is a rational number, which is the decimal is approximately 2.718, blah, 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 blah. Example for a natural log and log of a common log would be log base of 10, 100 equals 2, which basically means the same as log to 100 equals 2. Basically, you're just taking the 10 out because you assume it's there. E to the 3x equals 50. It will be the natural log of e to the 3x equals the natural log of 50. When you're doing the natural log and you put e to the 3x, the e would cancel out. So the e and the natural log, well, the e will cancel out because it's the opposite of the natural log, so it would just be the natural log of 50. Time to do another problem. What is the base of log 10,000? The base of log 10,000 would be 4, and I say it would be 4 because 10 to the 4th power equals 10,000. That's how you get in the base would be 10. It's 10 because there's nothing there. Solve the problem. The natural log e to the 4.5 equals y. E y equals e to the 4.5. So y would equals 4.5. And the natural log e to the 4.5 equals 4.5. If you haven't already guessed already, logarithms can have decimals. Logarithms can have decimals like 2.5, 6.36. Example, what is log 10? Well, basically, if you haven't guessed already, which is common law, you can just say log 26. Using your calculator, which I don't have present with me, you would press log and you would type it in 26 and you would close and then it will be 1.41497. The logarithm is saying 10 to the 1.141497 equals 26, which is n. Negative logarithms. A negative logarithm means how many times to divide by a number. An example, what is log 8? Log base of 8, 1.125. So it would be I messed up the slide, I'm sorry. Yeah, I'm just gonna see this stuff. The laws of logarithms. The first log you can't see because it's kind of blurry. The log of 1, which would be 0. And once you have the log of 0, it basically means that it's undefined and it will always forever be 0. The log of b, which you can't see, would be 1. So basically this is just saying the log and the log base of b times b equals 1. So if you have log b equals 1, that's basically what it's saying up there. So you have log 3 of 3 equals 1. So basically it's saying if the base and the argument are the same, that will always be 1. As long as the base and the argument is the same with the problem, the answer will be 1. Product. The product rule for log states log base of b x or y equals log base of b x plus log base of b y. An example would be log base of 5, 2 times 3. So the answer would be log base of 5, 6. But going back to the problem, it would be log base of 5, 2 plus log base of 5, 3. Now this really, is log base of 5, because here you're adding. Product basically means that you're adding. So you're adding this to the add the two bases to get log base of 5, 5, excuse me. Quotients are basically the same except for you're doing subtraction instead of addition. And the quotient rule would be log base of b x over y. And that would be log base of b x subtract log base of b y. An example would be log base of 3, 5 over 7. And if you haven't guessed already, it would be log base of 3, 5 minus log base of 3, 7. And that's the quotient. Reciprocals, it would be log base of b 1 over x. When you pick up reciprocals, you tend to think of one of the x anyways. It's basically the same thing with this concept, except you would be using log instead. And it would be log base of b 1 over x equals negative log base of b x. An example would be log base of 2 1 over 7 would be negative log base of 2 7. And 7 comes from right here, the x place of the equation or function. And you go right here. So basically that's reciprocals. Powers. The law states log base of b x to the n equals n log base of b x. An example would be log base of 3 2 to the second. And we'll be written as natural and then on this side of the equation is 2. So it'll be 2 log, the base never changes, base of 3 equals x. And the x is the big number, and that will be 2. So the answer would be 2 log 3, 2. And that's how you use powers. Log for logarithms. The other rules and properties for logarithms, which I found, in that I decided not to press the issue that much, but there was just some that you would use, but not as commonly as the laws of logarithm would be the logarithm base switch rule, which is used, which you can see up here on this side. It's log base of a b equals 1 over log base of b equals derivative of logarithms. The derivative of logarithms is basically 1 over the natural log of x. Whenever you think of the derivative of logarithm, that's what you think of. The logarithm base change rule states log base of a, b equals log base of c, b divided by log base of c, a. And the logarithm of 0. The natural log states log a x equals the natural log of x over the natural log of a. For the logarithm base which rule, the base b logarithm of c is divided by 1 by the case logarithm c b. For example, in the first one, logarithm base which rule, it would be, of course, write the formula out. Log of a b equals 1 over log of a, no, I'm sorry, log of b, a. The example would be log of 2, 8. Basically, as always, it's a bunch of things that will be log the base, which will be the same base as the question states, log of 2. No, sorry, it would be the log of 8. Right here it states for the log of 8. And the base would be 2. I have an example for the logarithm base change rule, which states log of a b equals the log base of c b over log base of c a. An example for this would be log base of 3, 5. And these would be log 5 over log 3. If you look here, the rule states you have to use the log for b, and b for the equation given will be 5. So that will go to the top, and then the bottom state calls for a, and a is the log, is the base for the equation that is given. So that goes to the bottom, so it would be log 3. This concludes my presentation on logarithms. I hope you learned something. Thank you.